Yeah. And it's also here memorized under this.
If you hit the little thumbtack,
yeah.
Open a new tab again. If you hit the little thumbtack to the top left of like the little dictionary,
Right here.
Yeah, just click that. Now every time you open a new tab, the one, so it's blue. So now every time you open a new tab, that'll stay there.
Okay.
Always.
All right. Good. Pictures.
Oh yeah.
Okay, I can't use that.
I choose you.
I'll take this.
Oh my God! Something else. Oh, I forgot something else. I forgot.
You just pull one out of his bucket.
Center?
Sure.
Sure, those are his brothers. Oh, yeah. Those are my doubles. Your doubles? Yeah. What? Those are all my doubles.
Oh, wait, you played the game without watching them?
No, I'm saying
that
one
one
double.
thing.
Don't be a hater, okay?
That one was made to be stepped on.
What was it you said on?
Popcorn eggs when they serve.
No, beat it.
Oh.
Which one did you grab? Okay. You want all night?
Don't judge.
Judge. Why not? Why not?
What?
Why not? But why not judge?
Why not judge?
Yeah, why not?
That's a very good question.
You make judgments all the time, right? That's good food. It's not good food. I should go to bed. I should get up. I mean, these are all judgments, right? That's a good person. It's not a good. Those are judgments all the time. We make judgments. I should do this. I shouldn't do that. You can't go through life without making judgments.
I'm here. All of them.
Let's see.
Wait, Stu, what'd you get? Oh, yeah.
Once you get
Oh, you better find it too.
I should, if he's in here. I know I have extra toes out. But
No.
why is he not in here?
Okay,
I know I have like 3 toes out.
Why did you bring your butt one?
He might win. I just have too many.
Ah, here it is.
Give him away.
Isn't that cool?
Okay.
That's awesome.
Yeah, isn't that a cool picture? I gotta turn the light down here in the front.
I'm not pulling it.
Alright, there's. Can you see it? I mean, can you see it?
It is a scary monster clown.
It's the hexagon. That's a,
Oh, yeah,
this is a
hexagon.
It's not so clear on the screen. I'm gonna try.
Hexagon though.
Let's magnify the picture. There it is.
Wow.
Where's that at?
That's the north pole of Saturn, I think. Isn't that cool?
Not on the south, right?
Not on the south.
What are the gases around that?
Those are known. I don't know what they are. But that hexagon just is fascinating. What is that? And of course, let's see. We could. The Earth on this scale would be. Yeah, not real small. I think it's something like that. It would be about that size on that scale.
But that's what's up. See, we got size on it. You see, if the moon was there, they would be on there.
like mind blowing if you really think about it.
Oh, it's fascinating and mind blowing and just wow, that's cool.
Just because Jupiter big don't mean nothing. We take them down.
Okay.
We got. I don't think that works that way.
Look at Jupiter like protect us from a bunch of asteroids.
Yeah.
Okay, so we're here to go over the review problems for you. I want you to don't turn it in. This is purely for your own sake of practicing. We're going to go over them here in class. I want you to correct your homework. And repetition is really a good thing for many of these things. Once you have it down, it's good for you to go back and repeat. But what I want you to repeat is the steps in reasoning, because I'm not going to give you this problem exactly on the test. I'm going to make a variation of it that's going to be different in some way. And if you just remember the answer, you're going to remember, well, it's not going to apply. So what I want you to practice are the steps in reasoning. So I propose that we start with the last and move forward, right? Does that make sense? Yeah, the last is the most recent, and so we move forward from there. Okay, now this problem involves a block sliding up a ramp, so it's given an initial kick, some initial velocity up a ramp, and you're given certain things: the mass, the angle of incline, the acceleration of gravity, and the coefficient of kinetic friction. Kinetic because it's sliding. So what are there? 5 things here. And what you're to determine is the distance it travels until it stops. So this block is going to slide some distance d up the ramp, and you want to calculate that distance. And that distance is going to involve the mass, the initial velocity, gravity, angle, coefficient of friction, possibly all of those, maybe not all of them, but it's possible they will all be involved. So I know this has some significance in Shanghai, right? The very last card you put on your forehead, nobody sees. I mean, everybody sees your own card. Anybody play Shanghai? It's got other names. Yeah. All right.
Is it too much grease on my head?
Okay. So, 2 ways. I want you to know both ways. Way 1 and way 2. Way 1 is by forces and the laws of motion, right? Newton's second law. Second way is energy. That is the work-energy theorem. You can calculate the distance both ways. I want you to be able to do it both ways. And you want to be able to demonstrate you get the same answer both ways, right? I might ask you to do both ways on the test. Maybe for the same problem, maybe I'll ask you to do it on one setup, do it by forces, on another setup, do it by energy, so you can't compare the two. So you have to be confident in getting them both. All right, so let's do way 1 first. Way 1 has the added advantages that it's easy to calculate the time to stop as well, although it is a little bit more work than way 2. Way 2 is fewer lines. You get the distance with fewer lines. Has the advantage of maybe you make fewer mistakes because there's less algebra. So way 1, what's the first thing I want to do? First step in these problems. So actually, Ms. Swanson, I think you didn't get a chance last class. I felt bad for you. We did everybody else in class but for you, so I'm going to start off with you today. So what's the first step?
You figure out, we're doing the forces, right?
Yes.
So you draw a free body diagram and
Right.
see the direction.
Good. Force diagram. So I'm going to draw the table here. Here's the block. So please tell me, what are the forces involved on this?
There's normal going upward, mass times gravity going kind of that way, yeah. And then friction is opposing motion.
So it's down the ramp.
Friction.
Yeah. And we know the magnitude of the force of kinetic friction. The magnitude is mu kn, right? But we don't yet know the normal force until we go through an additional reasoning. The normal force is whatever force is required to keep it from falling through the table, but we don't know what that is yet, so we work it out. Very good. Okay. Mr. Kelly, what's the next step? After I've drawn the force diagram, what's the next thing I want to do?
Well, if you get your coordinate system,
Thank
and then
you.
you assign the forces in relation to your coordinate system.
Good. So there's an obviously easier coordinate system to choose here, an easiest coordinate system. You could choose a coordinate system where x is horizontal and y is vertical, but that's not so convenient because then it would move in a combination of x and y, right? It moves some in the x direction and moves some in the y direction. So a convenient coordinate system is to align it with the natural motion of the body. So let's pick x and y to be aligned with the ramp. And then there's no motion in the y direction. It makes it easy because we've got only motion in the x direction. So I want to see, in your diagram there, you can indicate your choice of coordinates. And then we want the forces in each of these directions. So in the y direction, so the force in the y direction is going to be the total force in the y direction. I have three forces. Each one of these possibly could contribute a component in the y direction, but one of them doesn't. Which of the three forces has no component in the y direction? Right. Kinetic friction has no component in the y direction. And so it's, you know, this trig function has got to be cosine or sine, right? It's got to be one of the two. So you could write down a little triangle and verify, which you can do over here on the side. For example, here is gravity, and then I have my coordinate system is aligned parallel and perpendicular to the ramp. And so then I want to look at the component. And this angle right here is theta. So this is mg. Then this is mg cosine theta into the ramp that is perpendicular to the ramp, and parallel to the ramp, inclined back along, downhill along the ramp, mg sine theta. And you can confirm this by picking the angle to be 0, and then you know there's no force of gravity along the ramp. So that gravity along the ramp should correspond to sine theta, because sine of 0 is 0. Okay. All right. And then the next step is you want to calculate the total force in the x direction. So, Mr. Jackson, how about this?
Total force in the x direction. The force of friction is moving it down. Well, I mean, moving it negative in the x direction. And mg cosine theta?
What's
mg sine theta.
Sine theta, right? Look at our diagram there, sine theta. Okay, so how about the acceleration in the y direction is then mass times acceleration in the y direction. Is there any acceleration in the y direction in this problem? We've been told it stays on the ramp, so it does not accelerate. It does not. Not just is not accelerating it, or it is not moving. It does not move perpendicular to ramp. That's my reason for saying this. So that tells me the normal force must be mg cosine theta. And then we're left with the acceleration in the x direction is minus mu k in, which is mg cosine theta, minus mg sine theta. So I could simplify this minus mg sine theta plus mu k cos theta. And I cancel the masses, and then the acceleration is negative, which means it's decelerating. Notice the mass has dropped out of the problem. Mass has disappeared in terms of the acceleration. Why? Does that make sense? Mr. Vestal, why does it make sense that mass has dropped out of the problem?
Gravitational acceleration is independent of mass.
Yes, the acceleration due to gravity is independent of mass. And notice that the frictional force, so the gravity is proportional to mass, and the frictional force is proportional to mass. Why should the force of friction be proportional to mass? Kinetic friction.
The heavier something is, then the more it'll push down on.
Exactly. So as this is sliding, the force of sliding, the force of friction that resists the sliding is going to depend on how much force is applied to the surface that contacts between the two bodies. If I'm pushing down on it, there's going to be more friction, right? But if I'm not pushing down on it, there's still the weight of the book. So it's proportional to the weight, and the weight is proportional to the mass. So the mass drops out of the problem because all the forces are proportional to the mass. Okay. All right, so now we have, what kind of motion is this? Is this uniform linear translation, Mr. Tremblay? Uniform linear translation, uniform linear acceleration, or neither?
I would say it's uniform linear acceleration.
Yes, sir. So what's the condition for that, to just be uniform linear acceleration?
Well, obviously, that no outside forces act on the body.
Well, there are outside forces
Well,
acting on this.
Other than what's...
That would be uniform linear translation, right? This is uniform linear acceleration. There are clearly outside forces acting on this body. Mr. Flanagan.
Acceleration doesn't vary with time.
Right. Doesn't change with time or location, right? The force is always the same, and the acceleration is always the same. Now that holds as long as it's still sliding. If it reaches the top and stops, then the force could change, right? Because we got static friction for an instant. So our analysis has to end at that point. Once it reaches the top, we have to redo the analysis because we have presumed it's sliding up. If it reaches the top and stops, then that's static friction. If it starts to accelerate down the ramp, then we have to use kinetic friction, but the kinetic friction is going to be pointing up the ramp. And we've assumed that it's down the ramp. So, okay, so it's going to be uniform linear acceleration until it stops. Then we got to start over. We got to modify our analysis, extend our analysis. Okay, so if we have uniform linear acceleration, what is the velocity as a function of time? Ms. Watson, what is the...
Uniform linear acceleration?
Yes, ma'am. Velocity
So
is a
the
function.
acceleration can't be a function of time.
Correct.
In this.
Yes.
So would that just be negative g? I mean...
Close. It's not, but it's not negative g, is it? It's almost. So if I have an accelerating body, and the acceleration is uniform, which means that the acceleration doesn't change in time. So what does that say about the velocity as a function of time?
Velocity would be 0.
Is the velocity 0 if it's changing, if it's accelerating?
Well,
Velocity.
Because if you had, like, I'm thinking of it in terms of, like, a position formula, like, equation.
Yeah.
And so...
But I want the velocity equation.
Yeah, but if the acceleration isn't just a constant since it's not a function of t?
Yes, ma'am. Okay, do you want to start with the position then and work back from the position? So what would be the position formula?
It would be x naught plus v naught t.
Yes.
Plus, oh, so it's not minus 1/2 gt squared?
Well, it's ax, whatever a is, whatever the acceleration is. The acceleration in this case is this. So it's minus g with that stuff in the parentheses.
Okay.
But so we could write all that, but I'm going to recommend that you don't keep writing that. That's a long thing to keep writing, and the more steps that you take where you write that stuff over and over again, the more likely it is you're going to make a mistake. Just copying it and simplifying it will also be more complicated. So just keep it as ax for now, and then at the end you want to write it in the end. You want to write it in terms of these variables, right? We want to write it in terms of those variables. But for now, let's just keep it as ax, and then at the end we'll substitute for ax. Okay, now if that's the position for uniform linear acceleration where ax is a constant, what is the velocity?
It's going to be v naught plus 1/2 ax t squared. I mean, ax t.
Thank you. Good. Okay, now Ms. Ma, if we know the velocity, let's make a plot. Let's make a graph of that velocity. What does that look like in time here? Ax is negative, remember. It's decelerating. So what does a graph of that look like? Ms. Ma, what would you say the v of t, if I were to make a graph of that?
It's going to be a straight line with a negative slope.
Yeah, right. Bingo. Okay. Starts off v naught, that's the initial velocity. And what's the significance of that point? Right.
Which point?
That point right there.
Is that the point where it reaches the top of the ramp and it stops moving?
Exactly. Yeah, it's where it reaches its highest point on the ramp, right?
Okay.
So that's where it stops. So that's the time to stop, isn't it? That's how long it takes to stop. Okay, so how do we find the time to stop? Well, we use this, that intersection where V intersects the time axis. In other words, where the upward velocity is 0. Right? So V of t stop is 0. So t stop is going to be minus V naught over AX, and that looks a little funny. You might think at first, whoops, my time is negative. Wait a minute, that's funny. But remember, AX is negative. So if I want to go ahead and substitute in here V naught over G sine theta plus UK cos theta, there we go. That would be the time to stop. That's bonus, right? We weren't asked to find the time. That's bonus. But actually, we need it in order to find the distance. Everybody okay on that? Now let's check the dimensionality of this. It should be a time. So we have velocity. What's the dimensionality of velocity? Length per time. How about acceleration is length per time squared? That's g. And all those trig functions and mu k and stuff are all dimensionless. So that, in fact, is time. That's good. Let's do a common sense check. If I take friction away, does that increase or decrease the time? If I get rid of friction, does it take longer or less time, shorter time or longer time to stop? It's going to take longer, right? It's just gravity that's slowing it down. So if I set mu k to 0, the denominator gets smaller, the time gets bigger. So that's good. And you could do something else like set the angle of the ramp to 0. Put the ramp down. So here's a couple of common sense checks. So this is dA. Common sense. Let's try mu k to 0. No friction, so t stop increases. That's good. How about theta goes to 0? That means the ramp is on the table. It's horizontal. Gravity is not assisting the deceleration at all. It's purely friction. And sine theta goes to 0, so it's just going to be V naught over G mu k cos theta, and cos theta is 1, so it's going to be V naught over G mu k. Seems right. It's just friction. And there, suppose I turn off both. That would be T, rather, excuse me. T stop would be V naught over mu kg. That seems reasonable. And how about theta goes to 0 and mu k goes to 0? In that case, T stop would be divergent, unlimited, so it takes an unlimited, it never stops, it never slows down because there's nothing slowing it down, right? So T stop diverges. It's unlimited time to stop. There's nothing slowing it down. Okay, good. So that makes sense. Good. Okay. And remember, I give extra credit for this kind of stuff, dimensional analysis, common sense. If you find a mistake, see, there have been some, actually, you're pretty good about trying dimensional analysis now. That's good. And some common sense. I see a few people trying that out. That's been pretty good. I want to see more of it. But suppose you do the dimensional analysis and you get an answer that doesn't fit. Suppose you're trying to calculate a time and it comes out being a length. Don't just go blithely ahead. Now you might think, well, I've made a mistake, but I'm running out of time, so what am I going to do? At least write on the paper there and say, this should be time, not length, but I'm running out of time, so I've made a mistake somewhere. I realize that. But don't just, okay, see, the other problem is people would like to hedge their bets, so they'll write down something and think, well, this isn't right. And they think they've got their bases covered, right? They either got the answer is right, or they've hedged their bets by saying this is not right. That's not going to work. I want a specific answer. This should be time, and my dimensional analysis tells me it's length, for example. Okay, that's a specific answer. Okay, you've got a specific thing wrong. Don't just kind of say, well, this can't be right or something. That's not going to cover it. Be specific. What's that, Mr. Jackson?
I said the dimensional analysis is broken.
Yeah, it could be. That could be. It could be that your answer is right, and somehow you messed up the dimensional analysis. That could be. But they can't both be wrong. No, they could both be wrong. They can't. If they disagree, they can't both be right. That's what I meant to say. They could both be wrong. If they disagree, they can't both be right.
Yeah, you can. You can just have a bad argument.
Yeah. Okay.
You can write about something else.
All right, but we're not done finding the answer here. But notice that the time to stop here has been reduced to all of those variables that I listed in the problem at the beginning, right? M, V naught, G, theta, mu, K, and it's just an accident in this case that M has dropped out. An accident meaning, in this case, because the forces are the way they are, they're all proportional to mass, and so they all drop out. The mass drops out. Okay, but now what I need is the distance, and how do I find the distance? So, Mr. Fanning, how do I find the distance now?
You integrate the velocity equation, dmt position.
Yeah, and which is what Ms. Watson did for me here, right? Did for us earlier here. We've got this. And so given the x as a function of time, and we're looking for the distance from x naught. So we could set x naught to 0 here and just look for the additional distance it moves. So we want to substitute the time in here that we've got. And this is where it's helpful to keep keep it simple here by using ax. I'm sorry, t times stop is v naught over ax. Okay, and don't write out the full value of ax in terms of all those things from the beginning of the problem. It's a mess. So let's write d here. I'm sorry, there's a negative sign here. Remember, ax is negative, so this has a negative sign here. So d and t stop squared is going to be v naught squared over ax squared. The negative sign goes away. So then I have minus a negative v naught squared over ax plus v naught squared over 2ax. Or in other words, a half. So I have a negative 1 and a half, and if I combine those together, I get v naught squared over 2ax. I have a negative amount, and then I have half of it positive, so I get a positive amount. And now I can substitute in, there's a negative here. And now I can substitute in my expression for ax. And now this is my distance traveled, distance to stop. And again, I could do dimensional analysis and common sense check, which I won't do now, but worthwhile thing to do. Way 1 takes a little while, doesn't it? So I'm working at it pretty quick here, and I'm talking maybe more, so I'm slowing it down a little bit, but it does take longer. There are more steps to get to the distance traveled. But you also find that the time, that's a bonus, which we wrote up here, so that's a bonus, the time stop. And if I ask you to calculate the time, really, as far as as we've discussed in this class, you're going to have to do this method. You're going to have to use forces and acceleration to find the time. You can do it through the energy argument, but we haven't discussed how to do that. It involves a little extra work. Okay, that's way 1. Let's try way 2.
Doing that, does that take just as long as the force method?
Yeah, just about, right.
Okay.
But in this particular case, it involves integrals, and you have to have a good table of integrals in your head or at handy. It involves integrating. And, okay, way 2 is the energy argument. So, Ms. Shaven, what is the work energy theorem?
Work done is the change in kinetic energy.
And the work in that case is work done by what forces?
The force of friction. Okay. Not the force of friction.
Not the force of friction, good.
the wrong one, the other ones.
Yeah.
So the normal and gravity.
Yeah, and friction. It's all of them. So Ms. Shaven is confused, I think, and she's not the only one probably confused about this. There's another form of this. I could take another form of the work energy theorem, which is just the work of friction. Well, the normal force is not really even a conservative force because there's no displacement. Let's before we go here, let's just recognize the work done by the normal force. Does the normal force do any work? No. Yeah, it's because it's perpendicular to the displacement. So in this case, the normal force is 0. So really, the only work we're concerned about is gravity and friction. Okay. Now I could write it this way, where instead of the work due to gravity, I write the potential energy of gravity, and I combine that with the kinetic energy. And so this would be a total energy. I could do it. So two different forms of the work energy theorem. The first one is the more general one, but the second one involves the total energy. So sometimes you might want the second one, but you need to be clear on these two, that they are in fact the same thing, just expressed a different way. And which one do you want to use in a different case? As long as you use it correctly, it doesn't matter. Okay, so let's do the first one here. I'm going to opt in this case to do the first one, where the work is the work due by gravity and the work due to friction. So what is the change in kinetic energy for this problem? Well, it's the final kinetic energy minus the initial kinetic energy. Does it have any kinetic energy at the end of its run?
No, because our function is for when it gets to the top.
Right, we're looking for exactly. So we're looking for the distance it comes to rest. Then we're looking at that point where there's no final kinetic energy. So it's all initial kinetic energy, and it loses all of it. Loses 100% of its initial kinetic energy. So the initial kinetic energy is 1/2 mv0 squared. So the change in kinetic energy is, it loses all of it. And how about the work by the frictional force? You want to try that, Mr. Covington?
It'd be mu sub k mg cosine theta x, right?
Good, thank you. Yeah, and we'll say d because that's what we use for the distance traveled. Right, excellent. Where you've used this fact, and you should make note here, if you're doing way 2, that you've figured out what the normal force is. So you have to give, this really should be here, the normal force, this is in, and you have to give me an explanation of why it is that the normal force is mg cosine theta. And whereas way 1 up here, we've figured that out here, that there's no acceleration in the perpendicular to the ramp. So you should invoke that in your explanation. Okay? Is it positive or negative? I'll let Mr. Covington.
Negative.
Yeah, and why does that make sense?
Because it's working against the force that initially put it towards going up the ramp.
Yeah. Force of kinetic friction. Kinetic friction always does negative work. Never does anything but negative work. It could do 0 work if it's not moving, right? But then it would be static friction. So. Okay, gravity. Mr. Creer, how about gravity? What's the work due to gravity?
Negative g sine theta.
All right, that's the acceleration. That's not quite. That's not even. Yeah. Now I need a distance, and I need a mass. Yeah. So it's the force of gravity parallel to the ramp, and it points downhill. So and the motion is uphill. So the work due by gravity is negative, like friction in this case. Does gravity always do negative work? No. If it's coming down the ramp, it will be doing positive work. So if we flip this problem, have it sliding down, kinetic friction will still be doing negative work, but gravity will be doing positive work. Okay, now that gives us, then putting this all together, the loss of kinetic energy comes about because of a combination of gravity and friction doing work, opposing the motion. And again, the masses cancel. And so now I can find, I solve for d is equal to v0 squared over 2g times sine theta plus mu k cosine theta. And that, in fact, confirms our way 1 answer, the distance to stop. It's that same combination. So we're feeling good. That sounds good. So way 2 is quicker here. We've done it in, I've wrote it out slowly, and we still got it done less than a page. Way 1 was an extended page. I kept having to extend to get it done. But I found the time to stop using a way 1, and so I got more information. Okay, so you have to decide from your arsenal of methods, you have to pick one that's appropriate. If I ask for the time to stop, you don't want to start off with way 2, I don't think. You can do it, but it's hard. It's more than you really considered in class so far. Okay, so a simple variation on this might be, let's start the block at the top. Yes, sir.
So if we define d to be the distance that it goes up the ramp,
yes, sir,
in the direction of the ramp.
Yes.
So then why would the frictional force why would the distance used for the frictional force be cosine theta d instead of just d?
Right. So remember, the frictional force is proportional to the weight, and that's perpendicular to the ramp. It's how much force is pushing the body into the ramp. And that normal force is proportional, then the normal force is perpendicular to the ramp, but the gravity, which is what the normal force is opposing, is not pushing straight into the ramp. Gravity is pulling down on the body at an angle.
Right.
And that's where that cosine of theta comes from.
Right, got it. Thanks.
The other thing that's there is the sine theta. And that's because the ramp is not going straight up, right? So the distance, vertical distance, is d sine theta. So it's traveling a distance d up the ramp, but the work done by gravity is only d sine theta because the ramp is inclined at an angle. And so it's not, the work done by gravity is only that which is the distance off the floor, the vertical distance off the floor. So that accounts for those 2 trig functions. Yes, and it's good that you stop to think about that. Why is it like that? Okay, and a simple variation would be to, say, start it from rest and find out how long it takes to stop, or find the velocity at the bottom. If I ask you to find the velocity at the bottom without asking for the time, you could use the work-energy theorem. If I asked you to find the time for it not to stop, to reach the bottom, how long does it take to reach the bottom, which is a distance d down the ramp? Then you'd need to use the force method. So that's a simple variation, and in this case, the force of friction is now resisting the motion because it's sliding down. So Fk is now in the opposite direction to gravity. Okay, that's a simple variation. Again, you could do way 1, way 2 on this. You should be able to do both ways. Any questions about number 9? Got a few steps in there. I might do something where I break it up into some steps, or I might specifically say do the force method using Newton's second law, or I might specifically say apply the work-energy theorem, since we just finished chapter 5. Okay, number 8 is really pretty simple. The work done by gravity on a body in motion, and the work done by kinetic friction on a body sliding on a table. Again, it's proportional to the normal force. It depends on the normal force. So you have to find the normal force to find the work done by kinetic friction. God bless. You want to go over number 8? Okay. Sure. Okay. The first part, calculate the work done by gravity on a body in motion. Well, that could be all kinds of motion, right? We have a body in motion. What's the work done by gravity? It's not very specific. Yeah, it's just how high it goes. The work done by gravity. If I know how high it goes, what's the work done by gravity?
MGH.
Is it MGH?
Negative MGH?
Negative MGH? Which is it?
Depends on which you said it's positive.
Well, if H is positive up,
Then
right?
it will be negative MGH.
Yes, negative MGH. Because if the body has moved up, the work of gravity has done negative work, right? Because the force of gravity is pulling it down, displacement is up, it's negative work. If it's fallen, it's gone from higher to lower, the work by gravity is positive. Or we could say this is minus mg delta y. How about that? That's even more specific. If y is the coordinate,
I like
delta y, that's really nice. How much change in a y?
That's such a nice triangle.
Okay, he likes that one.
Like dot, dot, dot.
Okay, it doesn't matter the path. It could be a projectile going, from a cannon, going like this. Doesn't matter. Okay. Let's consider for a moment the projectile problem. As giving a little variation on this one. Let's have the projectile shot from a cannon at an angle theta. Let's suppose it reaches its high point. What is the kinetic energy of the body at the high point? Somebody said very quickly 0.
1/2, because you still have.
No, it's still got velocity for
MGH is the potential.
So it's 1/2 m.
Oh boy.
Times the
It's still got velocity.
Kinetic at the top is nothing.
Times cosine.
It can't be nothing.
Potential is
The
in
order
zero.
is specific kinetic is nothing.
It's
The
got
projectile's still moving.
How about let's break it up into components here. So the initial kinetic energy is 1/2 mv naught squared, yes, but let's break it up into components along the x and y direction, right? It's v naught squared cos, so the vx direction and the vy direction, right? So does the velocity in the x direction remain constant? Yeah. If x is here, I should define my coordinate system x and y like this. So in the x direction, yeah, it doesn't change. So it might lose its vertical velocity, but it never loses its horizontal velocity. So the kinetic friction, the kinetic energy at the high point here is going to be that. Okay. Is the total energy conserved in this problem?
Yeah.
Why?
Because there is no non-conservative force acting
Good.
like friction or something.
Right. So how about potential energy? What's the potential energy?
MGA.
MGY, right? Where it starts off at y equals 0. Delta y is going to be just y. MGY. And so the total energy is going to be conserved. So that means 1/2 m, the velocity in the y direction, plus mgy is going to be equal to its initial value, which is v naught squared sine squared theta, right? That means the total energy is the same anywhere along the path. So it has an initial kinetic energy, and then it later becomes kinetic and potential. And so at the top, Vy is 0. So mg times y top is 1/2 m v naught squared sine squared theta, right? The vertical amount of the kinetic energy, the part that's associated with the vertical motion, is going to be traded off for potential energy at the top. Does that make sense? But the kinetic energy still maintains a horizontal piece, never loses that. Okay. So that's an example of applying the work done by gravity, because that shows up as the negative of the potential. All right, so let's look at kinetic friction. It's sliding to the right, let's suppose. So, and it slides a distance, d, from here to here. How much work is done by kinetic friction? All right, and now you have asserted here that the normal force, you asserted correctly that the normal force is mg, right? It balances the weight, keeps it from sliding. It keeps it from falling through the table or jumping off the table, whatever. It just balances those forces. So in this, you should, the vertical force is balance. All right, quick force diagram, normal force, gravity, force of friction. Normal force does no work because it's sliding perpendicular. Gravity does no work because it's sliding perpendicular. Friction is the only force in this situation, only force that does any work. Okay, how about the projectile problem? The range and time of flight. Absent air resistance. Air resistance we could try it sometime, but makes it a little bit more complicated, so we're not going to do air resistance. Just absent air resistance, can you calculate the range, time of flight? Here's a good variation on that problem. Suppose we put the cannon at the top of a cliff, height h, put the cannon here, and it's going to fire the cannonball at some angle. Let's suppose we make it horizontal just to make it a little simpler. What's the motion of the cannonball? Well, it's going to be a parabola like that, starting off at zero slope. Okay, now calculate the range. And the time of flight. That's a little bit different problem. It's a nice variation on it.
Is it shooting horizontally?
Yeah, let's suppose it shoots horizontally.
Theta is 0.
Can't you just say your initial y?
Initial y velocity is 0, isn't it?
I meant your position.
Yeah, sure. You have some freedom in the choice of coordinate system. You could choose y to be at the base of the cliff, like this, or you could choose y to be up here, whichever. Just make it clear what your coordinate system is. You have some choice here. Force diagram is very simple. There's only gravity. The impetus in the x direction is unabated. It just continues. And so it's just gain. It starts off with no impetus in the vertical direction, just gains downward impetus the whole time. So, and again, what you want to do in this case is to solve for the, say, the range as a function of the mass, the muzzle velocity, the height, acceleration of gravity, taking out any kind of inclination of there's no angle because I said the cannon is horizontal, but if we gave it an inclination, it could be some angle. And not surprisingly, the mass drops out of this problem also, but that's an accident again. All the forces involved in the problem are proportional to the mass, so it drops out. Okay, time of flight would be another thing to find. How long does it stay up in the air before it hits the ground? Okay. Do you know how to do this one? Good. So there was, for some reason, so I want to pass out your previous homework in the test, and I am sorry to say I forgot to copy the solution for the test, so I will do that and get it to you on Monday. Okay, I'm sorry that I did that, but there's one problem I want to go over here, because that did seem to be one that caught people on the test. I think that a lot of people were a little messed up by this one, and this was one of the ones at the end here, the very last one. Let's look at this problem. Okay, I want to find A1, A2, and T in terms of what? M and G. That's all that's left. So I want expressions for each one of these, A1, A2, and tension, in terms of what's left, M and G. I don't want A1 in terms of A2. I don't want T in terms of A1 and A2. You haven't solved it. So I want, when I say solve it, I mean eliminate the things I'm solving for in favor of the the ones that are left. In this case, it's just M and G. And that seems to have stumped some people. Okay, so let me say generally what's happening here. I want to preface handing out the tests here. So I'll get the solution to you on that on Monday, but I want you to try this again. Okay, this would be a good one for you to try. So it's straightforward algebra, 3 linear equations and 3 unknowns. Straightforward linear algebra. It's just a matter of realizing what it is you've got to do. So what's happening at this point in the course for a lot of people, this is the point in the course where I find that some people's grades have reached a minimum here on the tests, right? That does happen. And the reason for that is Chapter 4 and Chapter 5 is where the imperiometric is really starting to take hold, and you're learning how to do it, right? It's something that takes some understanding that you don't have to guess solutions. You just turn the crank. You've got to set them up right and then use the algebra and a little bit of calculus to figure it out. There's no guessing here. And also, like this one, you have to realize what it is that you're trying to do. You're trying to find A1, A2, and T, in this case, in terms of the other things in the problem. And like, for example, here we go. I said, I want, in this case, the distance to stop in terms of m, v naught, g, theta, mu, k, right? So you have to have in your mind what it is that's fixed by the experiment, suppose we say it like that. And then the things that we're looking for as a result of the kind analyzing the motion, in terms of the basic principles. So that expresses itself in the mathematics as knowns and unknowns. The knowns are the things the experimenter sets, what you do when you set it up, and the unknowns are the things that you're going to solve for as a result of the understanding how the motion is going to go, something that happens in the future after you do the setup. Maybe that's a way of thinking about it. Okay, so that's still kind of clicking. And at this point, I think most people are really starting to catch on. Okay, that's what I've got to do. And the reason that the scores on this last test, I think, will disappoint a few people is because that hasn't clicked for some people yet. And you'll look at this and say, no, I didn't understand that that's what I was supposed to do. Okay, so now I think it's going to start clicking. And I think I'm trying to encourage you here. Keep working hard. Don't be discouraged. I think if you work hard and you start to get the idea, your test grades will be coming up. But notice the tests are going to get progressively harder. And you really do have to understand what happened on this test 4, this test for that we got at the beginning of the week. You really do have to understand it. Study the solutions, and I apologize for not having the solutions for you to study today. I may scan them and send them to you. In fact, that way you can have them right away.
You can make it harder. We got you. We're docile. We can do it.
You're docile? Okay. You're, docile. Docile to your instructor. That's good. That's good.
No, we're docile.
Docile. I thought it said docile. Docile.
Well, that's actually a good adjective used in English.
Being docile to your instructor can be a good thing if it's if it's a competent instructor and so forth. All right, so I'm passing out homework and tests. Let me. I don't have this sorted by name yet, so let me pass out the homework here, and then I'll pass out tests for you.